So from the S parameter equation, you see this equation, we can find four parameters: S11, S12, S21, and S22. So if you put A2 equal to 0, I can find S11 and S21. So see here, if put A2 equal to 0, I can find S11 equal to B1 by A1. And see here, both happens at port 1. So I can call S1 as reflection coefficient at port 1. B1 is the reflected power at port 1. A1 is the incident power. So everything happens at port 1 itself, right? So I call it as input reflection coefficient or reflection coefficient at the port 1. S21, you see, I'm giving input A1 and I'm getting the output at B2. The S21 is called as transmission coefficient. Just see where is A1. A1 is here and B2 is here. B2 is coming out. So whatever I'm giving input, it is getting amplified and coming out. So I can call this S1, S21 as transmission coefficient, whereas S11 is reflection coefficient at port 1. Same way, if I want to find the other parameters, see here, if I put A1 equal to 0, I can find S22 and S12. S22 is B2 by A2. Since it is happening at the same port, I can call S22 as output reflection coefficient or reflection coefficient at port 2. And S12 equal to P1 by A2. See, P1 A2, I am giving A2 here and B1 is coming out. It is just like reverse transmission. So output side la I'm giving input side la I'm measuring it output. It is actually opposite to that of the conventional amplifying path diagram, right? So this last coefficient S12 can be called as reverse transmission coefficient, or sometimes they call it feedback, because when something comes from output to input, it is called as feedback, right? The S12 is also called as reverse transmission coefficient, or it is also called as feedback coefficient. In majority of cases, we'll take S12 to be equal to 0, because we assume the system does not have any feedback. The remaining three parameters are very, very important: input reflection coefficient, output reflection coefficient, and transmission coefficient of the system. Okay. Ideally, we expect tau 1 to be 0, perfectly matched, tau 2 to be 0, perfectly matched, and S21 is the amplifier gain. This should be maximum, as high as possible. Okay, so that is the actual requirement from the S parameters. So as we see here, S22 is the output reflection coefficient, S12 is the reverse transmission, and all the parameters are given here. So once you know the S parameter values, without knowing what is inside the network, you can analyze the system using S parameters. It's just like a black box. So if you know the four S parameters, 11, 12, 21, and 22, you just need not know what is the component inside the circuit which is going to give these S parameters. Okay, that is the beauty of S parameters. So without even knowing what is inside, just with the four numerical values of S parameters, you can completely characterize the system in a very perfect way. Okay, so there is no need for open circuit or short circuit in conventional high frequency circuits, because these S parameters do not depend on OC or SC condition. They depend only on the incident and reflected power. So measuring S parameters will ensure that the system is going to be always stable. Thereby, the potential for oscillation is going to be completely eliminated. Whereas I told you in the previous case, in high frequency circuits, if you try to establish open circuit or short circuit condition, there might be a chance that the device may go to the state of instability, or it may become unstable. But since all our focus remains only on the measurement of incident power and reflected power, so the circuit is going to be completely stable. And wherever you go in S parameters, we'll be terminating the load or source with